In this lecture, we're going to start looking at electric fields for continuous charge distributions. So let's talk about electric fields. For continuous charge distributions. Okay, so last time, or the last lecture, we discussed basically how to calculate electric field. Electric field E, P at a point is equal to the sum of I of all the charges, EIP. So this is the electric field from all the different charges. Okay, so what is that? Well, this is really equal to sum on I, okay, of basically K Q sub I over RIP squared RIP hat, right? If you want to basically think about this, you can basically just have some collection of charges, you just sum up all the charges to get the electric field. Right. So let's consider a different kind of charge. Let's consider continuous charge distribution, and to start we can consider a simple line. So let's imagine a line of charge. Okay? And this all the way goes to infinity, and this all the way goes down to minus infinity, say. And to basically make this a little more concrete, let's suppose the y-axis is in this direction. So that's basically the y-axis. And so let's go y to infinity and that minus infinity. Now let's imagine I've selected a point. Let's put my point P here, right? And I want to find what the electric field is at this point. Okay, well let's basically talk about how to set this up exactly. So we're going to need to know that this thing is going to be some distance L away from the line. This is distance L, right? And when we talk about distance L away, what that means is that basically this is this thing is the shortest distance. So what that means is it's going to be a right angle here, right? Okay, so I want to figure out what the electric field is at this point. Now, how would I do that? Well, if I were to think about this carefully, I can imagine that rather than considering as a line of charge, I consider basically let's say a bunch of charges like that. Okay, let's say I have line charges on the string. Okay, and what's going to happen is that I'm going to basically make these charges eventually smaller and smaller, but also close on space, bring the space between them to be smaller and smaller, until eventually basically it just looks like a line. Okay. And so this is basically the ith charge here has a qi charge, right? And is that basically y equals y sub I, right? Just some position there, right? Okay, so if I were to do that, let me think about what the electric field is. So I need to determine what RIP is, right? So RIP is going from the ith charge to position P. So let's go from this ith charge all the way to position P. That is going to be RIP, right? And that's going to have a special form associated with it, right? So first of all, if this is my y-axis, I'm going to have to call this my x-axis, say, right? And this is going to select this to be y equals 0, and then you can say x equals 0 there as well, right? So in that case, I'd rather figure out what RIP is going to be. RIP, well, I'm going to move in the positive x direction by distance L, so it'll be L x hat, and I'm going to move in the y direction by amount y sub I, so y sub I y hat, right? Okay, so that's RIP, vector. And so RIP, the distance, is just going to be equal to basically the norm of this thing, which is just, if this is a right triangle, you want to find the hypotenuse of this, L squared plus Y sub I squared. Okay? Simple enough. Okay? And if I were to try to find basically RIP hat, well, what's that going to be equal to? Well, that's just going to be equal to RIP vector divided by the distance, right? Because I just have to make sure that this norm of this thing is equal to 1. And if I do that, I can just literally write it down, right? So it's just going to be L over square root of L squared plus Y sub I squared in the x hat direction, plus, I'll divide this again, Y sub I over square root of L squared plus Y sub I squared in the y hat direction. Okay? So I have almost everything I need. I just need to basically figure out what Q sub I is. Alright, we'll discuss that a little more carefully in just a second. Alright. Okay, so let's go ahead and do this. Alright, so E of P is equal to, let's see, so I got sum of this, sum of I, K, QI over RIP squared. Well, RIP is the square root of L squared plus YI squared, so RIP squared is just basically L squared plus Y sub I squared. And then RIP hat. Okay, so I got to plug that part in now. Let's go and do that. That's just going to be L over square root L squared plus Y sub I squared in the x hat direction, plus now Y sub I over square root of L squared plus Y sub I squared in the y hat direction. Okay, that's very simple now, right? Okay, so the one thing I do need to figure out is what Q sub I is. Now, how do I do that? Okay, so let me imagine that this line has a charge per unit length. Right? And I'm going to denote this by symbol lambda. Okay? So if I sum length, basically it has some associated charge with it. So now, if I were to look at this thing very carefully, right, I can imagine that I'm going to take all the charges in this region and squish it down to one charge right there. Right? So what would that charge look like then? Well, then in that case, Q sub I is going to be equal to, well, this distance right here is going to be a delta y, right? So the total amount of charge would be lambda times delta y, right? Okay. Okay. So once I have this, I can go ahead. If I just equally space every charge to be delta y apart, then all the Q side will have this charge. Then I'm going to plug this into there again, right? So let's go ahead and do this. Don't forget the symbol, vector symbol there. All right. So let's write this thing down. E P is equal to square sum on I. Okay. Let's see. So there's a K here. All the Q's I said was lambda delta y divided by. Now let's figure out the rest. I can combine these together. L squared plus y sub I squared to the 3/2, right? I still need sum of I because I need to figure out what y sub I needs to look like. And then the rest of it is just going to be L x hat plus y sub I y hat. Okay, very nice. All right, so we're almost there, okay? Now, the only thing I need to figure out is the following, okay? Right. So what is y sub I? So y sub I is the position of this point, right? But you can think of this as the following. If I define y along this direction, then y sub I is simply just y, right? I'm just summing over all these different points there, right? So this is going to be equal to, right? So for every point it's y sub I. So I can imagine now that I'm going to take the limit where, so let's suppose, so y sub I is going to go to y, right? And now we're going to take the limit of delta y goes to 0. So when that happens, then all the cubes of I will nearly go to 0, right? All right. And so as a result, what will happen is that delta y gets shifted over to dy, and sum of I gets shifted over to an integral sign. All right? So let's go ahead and do that. So this thing now becomes, oops, e of p is equal to, now this thing gets shifted to integral, okay? K lambda, this thing gets shifted over to dy, divided by L squared plus y sub y, sorry, so that was y squared here, no I, 3/2, okay? And then it's going to be L x hat plus y hat, right? Okay, so now we're done, right? So we can read this as two things, right? So if we have this thing times this gives me the component of the electric field along the x-axis, so I could think of this as basically Ex. And this component will give me the electric field along the y-axis, right? Because it's multiplied times x hat and y hat. All right, beautiful. Okay, so let's go ahead and do this correctly. So let's get the right limits now. So I'm going to integrate along y. So I'm going to start at y equals minus infinity and going up to y equals infinity. All right. Okay, so with that in mind, we're going to go ahead and basically do this integral, all right? Okay, so let's just write that integral down once again, right? So this integral looks like this. E of p, I'm going to break it into two integrals, right? So k lambda L over L squared plus y squared to the 3/2 power x hat dy, y equals minus infinity to infinity, plus now the integral y equals minus infinity to infinity of second term k lambda y y hat dy divided by L squared plus y squared again to the 3/2 power. Okay? And again, as I said before, this is going to be Ex and this is going to be Ey. Now, as it will turn out, this term will be 0. Okay? So Ey will be 0. And there are two ways of showing this. Okay. Now, the first way of showing this is actually an argument, the symmetry argument, basically, right? So let's look at the picture again. Okay. So imagine there was some Ey component here. So let's imagine there was some Ey component right there, like that. Okay. It could be pointing up and down. I don't really know. It doesn't matter for this argument. Now let's imagine if I take this situation and I flip it. Okay. So I flip this thing along the x-axis. So now basically y infinity is at minus infinity, y at minus infinity is at plus infinity. And what will happen to Ey if I flip the entire thing? Well, Ey will flip over to the opposite sign, the opposite direction. Okay? But if I look at the situation again, nothing has changed. It is the same computation as before. So what that means is that Ey is equal to minus Ey, and that's only true if Ey is equal to 0, right? So the first way is by symmetry. So flip symmetry. This is actually called reflection symmetry. Okay. Okay. So if I reflect, or flip around x-axis, right? This implies Ey goes to minus Ey, but calculation is the same. Which is the same as saying the problem is the same. Okay, so I'll write this there, problem which implies, because nothing has changed now, that EY has to equal to minus EY, and implies that this negative EY has to be 0. So that's the first argument. It's just flipping. The second way of arguing is literally to do this integral here, right? So you could basically look at the integral, right? Integral is odd. Okay. Well, you got odd. Well, you look at this thing. This is y squared, so it's always positive, right? This is y, which basically flips sign as you go across minus y. And anytime you have an odd integral and you're integrating over even domain, basically it's the same amount negative as positive, that integral always turns out to be 0. Okay. So we can actually go ahead and actually do that. Okay. So if I write down the integral here, EY is equal to integral minus infinity to infinity k lambda y over L squared plus y squared to the 3/2 power y hat dy. Okay, I want to simplify this thing, right? So I'm going to let t equals L squared plus y squared, and then dt is equal to 2y dy. Okay, so if I do that, there's a y here or y dy there, and so you can convert this integral to something that looks like this: 1/2 to 2 goes to the bottom, and then I'm going to integrate this thing. I'm going to leave the sign in what I'm integrating over. Okay, and then so I'm not going to convert the limits yet, right? And then what you end up getting is that you get a k lambda y hat, and then the rest of it is just literally dt over t to the 3/2 power. Okay, so I know how to do this kind of integral, right? So this is just going to be, if I flip this thing, it's going to be, so you recall how to do integrals like this. Integral of x to the n dx is equal to 1 over n minus 1, and then that's x to the n minus 1, right? N plus 1, sorry. N plus 1. Okay. And so let's go ahead and look at this thing. So in this case, n is minus 3/2. So 1 over minus 3/2 plus 1 is a 1/2. So that's a minus 2. So minus 2 times a 1/2. Okay. And then there's a k, a lambda, a y hat, right? And then the rest of it is just going to be x to the n plus 1. So that's going to be t to the n plus 1. N is minus 3/2. So minus 3/2 plus 1 is minus 1/2. So that's going to be basically 1 over t to the 1/2, which is, and t was this thing. So essentially t to the 1/2 is L squared plus y squared. And let's not forget our limits of integration. Integrate at y equals minus infinity to infinity. Okay. So you can go ahead and do this thing now. Okay. This will all cancel out. So it'll basically be minus k lambda y hat. Okay. And the first one will be 1 over square root of L squared plus basically infinity squared. Okay. Minus 1 over square root of L squared plus minus infinity squared. Okay. 1 over infinity is always 0, but on the other time, but you can also say that these two terms are exactly identical to each other. So in fact, this entire thing goes to 0. And so this has to be 0. Okay. So that's the two ways of arguing it. Okay. That basically gives you EY now. Okay. Now you got to do EX, right? So EX is not so simple, but it's actually not that hard either. So let's go ahead and do EX now. Okay, let's write down what EX is going to be first before we continue. So EX is going to be equal to, let me get this right here. Integral minus infinity to infinity. Y equals, I really like this nomenclature, right, by the way. So I use this all the time. is basically when I integrate, I keep track of what my limits are involved. So that way I can do things about converting limits until the very end, right? So it's a useful tip. You may or may not like that. K lambda L x hat divided by C L squared plus y squared to the 3 halves power dy. Okay. All right. So let's go ahead and do this integral, right? So this is a tricky integral, okay? And so whenever you see an integral like that, you're gonna have to use a trigonometric identity, right? But I don't generally like most trigonometric identities. I like hyperbolic sinh identities, so I'm gonna use the following. So I'm gonna let y equals L sinh theta, right? Why do I like this? Because I know what dy is going to be equal to L cosine theta d theta, right? The beautiful thing about sinh identities is that if I take derivatives, I don't ever get this minus sign that pops up if you take a derivative of cosine, all right? For instance, the derivative of d cosine d theta d cosine theta d theta is going to be equal to minus sine theta. You never get that. It's just something very nice. Always positive signs, right? Okay, so let's go ahead and do that. So this can be equal to, let's get this right now. Let's see, so again, I keep this thing, y equals minus infinity to infinity, k lambda L x hat, all right? Now dy was this, so that's just going to be L cos theta d theta divided by now this thing. That's just going to be I can factor out the L squared out of this thing, so it'll be L cubed, right? So L squared through 3 halves is going to be L cubed, and the rest is going to be 1 plus sinh squared theta to the 3 halves power, right? All right, so this term here is just cosine squared theta, and cosine squared theta is at 3 halves, it could be cosine cubed theta, right? So this is just going to be something pretty simple now, and let's just get all the L's correct. So see, so the L here, so 1, 2 will eliminate 3 there, so it'll be L to the 1, okay? So it'll be K lambda x hat, I'll move all the constants down front now, over L, and then the integral y equals minus infinity to infinity of cos theta over cosine cubed theta d theta. Okay, so this will limit that, turn that into a 2, right? Okay, so this thing turns out to be something not super difficult. Okay, this thing turns out to be equal to k lambda x hat over L, right? And then the rest of it is just going to be integral of y equals minus infinity to infinity of secant squared theta d theta. Okay, secant squared theta, the integral of this thing is just going to be tangent theta. All right, so it's going to be k lambda, keep the x hat still, over L, okay, tangent theta evaluated between basically y equals minus infinity and infinity. All right, okay, so now we just got to be a little bit careful about how we're going to do this, right? Okay, what's the right way of saying this thing? So there are 2 ways of getting this one, right? The first thing is that you can actually write down what tangent theta is. So tangent theta is sinh theta over cosine theta, all right? Okay? And then you recall that basically y is equal to L sinh theta, which means that sinh theta is equal to y over L, right? Okay, Now if you do that, okay, you get something that's relatively simple. Okay, you can write this one as sinh theta over square root of 1 plus sinh squared theta. So that's going to be basically y over L divided by square root of 1 plus y squared over L squared. Okay, that's one way. And then you could evaluate this thing directly there. All right, we'll do that first. Okay, so let's put that thing there. So at y equals infinity, we take basically y equals infinity, take the limit y equals infinity. This implies that tanh theta is equal to, let's see, so this is infinity, this will factor out to infinity, so it'll be infinity over infinity, which is be 1. Okay? Now, if you take it to be y goes to minus infinity on the other hand, right? Then this is minus infinity. This thing will work out to be square root of infinity squared, which is infinity, and so this b equals to minus 1, right? So that's actually pretty simple, okay? The other way to look at it is understand what tanh theta looks like. It kind of looks like this. That's a plot of tanh theta. Okay. And it goes to the limit plus 1 and basically minus 1, right? And then sinh theta, which is basically what y is going to look like, looks somewhat similar. Actually, it looks like this, and then explodes toward the end like that. Okay, so this is sinh theta, right? Okay, and so basically what happens is you're about at y equals infinity. Basically, theta is infinity, right? And so theta is infinity gives you a tangent of basically 1 and minus 1 respectively. So that's the other way to look at it. Just look at the plot, right? This is a little more straightforward to do, right? But anyway, in any case, this answer is extraordinarily simple, right? And so we can literally plug this in now. K, right? Lambda x hat over L. And the first term is that y equals infinity. That's just 1. Minus y equals minus infinity, that's minus 1. Right? So that comes out to be something simple. 2k lambda over L x hat. Okay? A beautifully simple result. Right? At the end. Okay. Alright. So that's basically that distribution, right? Okay, so it's actually quite a bit complicated, right? So you start out with a line, you discretize a bunch of points, you wrote what the integral is then, and then you proceeded to solve the integral, okay? So basically, you argue two pieces of it, there are two pieces of it, you argue one piece away, right, which is EY, and then you basically solve what EX had to be, okay? Right? So, like, it's not horribly complicated, but it's definitely one of the more complicated things that we will do in this class, right? Okay, so let's go ahead and do a slightly different exercise to basically to basically illustrate these points, right? So the second example I will consider is the following. Okay, this is a electric field around a charge ring. Okay. Now, it will turn out that like this integral, this will also devolve itself into an integral, but it will be much simpler than the previous one. And in part, basically, in the previous case, we consider infinite line, which is extremely easy to visualize, but a little more difficult mathematically to calculate. Here, we're going to do something a little simpler. Right? We're going to consider the following. Let's basically do a field around a charge ring. So here's my charge ring here. Okay, right? And you can imagine that this is in the let's think about this. Let's think about something above the axis along the axis of the ring, along the x-axis. And so this ring is basically in the YZ plane, for instance, right? And this is my position here, P, which is I decided at some position X, right? Relative to to the axis here, right? So let's say this is going to be x equals 0 here, right? Now this charge ring has a radius, capital R, all right? And it will have a total charge Q now, okay? Now this is different than our previous example where we had a charge per unit length here. If I asked what the total charge of this line was, well, this goes to plus infinity and minus infinity and plus infinity. So anything, the length times the length per unit charge, the length is infinity times the length per unit charge will give infinite charge, right? Also like pretty horrific in terms of like things to think about, right? This one's simple, right? This ring has finite length, and so as a result, I can define a finite charge on it, right? But nevertheless, I would still think about basically a charge per unit length, okay? Let me define charge per unit length here. Whoops, length. And this will be called lambda again, and it'll be the total charge over the total length, which is basically total charge over the circumference of a circle. That's 2 pi r, right? Okay, great. So, this is simple enough. I'll just do it first, and then we'll worry about something else. Okay. I unfortunately skipped the example, but I'll just return to that. This is actually pretty simple. Okay, so let's go ahead and do this one. So, E, P, well, we decided that this was going to be sum on I, K, Q, I over RIP squared, RIP hat, right? So, I'm going to basically look at this from an integral point of view first. So if I take Q sub I goes to infinity, so infinite number of charges, right? But keep it finite. Then the sum goes to integral, and Q sub I goes to dq, right? So that makes it a lot easier. Let's go ahead and write that down now. Okay, so E, the vector here, P is going to be equal to integral K dq over R P squared R P hat. Now I have to be careful, right? Because embedded in these things, the laws depend on which particular Q, infinitesimal Q, that I want to think about, all right? Okay, so let's look at this thing, all right? And if you look at it, you're going to get basically three components of electric field. You get electric field along the x-axis, this is EX, and you get electric field along the y and z axes, all right? Now, I'm not going to make you compute three different components of this thing, though in principle I could, right? However, two of these components are going to be trivial, right? And namely that they're going to be zero. So how are we going to show that? So the way you show that is that what you will notice is that this is symmetric around this x-axis. I can spin it around, right? So if I have some EY, and EZ, right? If I spin it around, what will happen is that all the EYs and EZs could be mapped to each other. Namely, if I spin it around by 180 degrees, all right? So if I spin by 180 degrees, that means that basically EY goes to minus EY, and EZ goes to minus EZ, right? And if this is true, if I look at it, and if I look at the situation, if I spin out, nothing has changed, right? And problem is the same, right? Which means that basically what I conclude is that EY has to equal minus EY, and EZ has to be equal to minus EZ, right? Only way that can happen, these are all zero. Okay, so boom, I'm done already with all. All I need to compute now is EX. So I need to compute EX. That's just EP dotted with the x hat direction. So that's just going to be basically equal to integral of K dq over RP squared, RP hat dot with x hat. All right. So I need to compute this quantity here. All right. Okay. Now I write it like this basically because it turns out to be much simpler this way. Right. You'll see why in a second. right? So let's go back to this thing again, all right? Let's write down what RP is going to be. So for every infinitesimal charge up here, I'm going to have a direction that links that charge to the position P. So this is going to be RP vector, right? And then, so RP vector, well, let's see. So RP vector is going to be something, right? Dotted with x hat. What's that going to be equal to? Well, this is basically, RP vector is going to be something x times x hat plus some garbage in the y hat and the z hat direction. But I only care about what's going along x hat because y hat, x hat dot y hat is 0 and y hat, x hat dot z hat is 0, right? So the only component that will matter is this turns out to be basically x, that just turns out to be x, right? Now the second thing is that I need to figure out what RP is going to be, right? Okay, so RP, the distance, well, this is a right triangle again. Wait, hold on, that's not right. This is a right triangle again. And so basically what we have is that this is going to be equal to the square root of, well, one length of the triangle is going to be r squared. The other length of the triangle is going to be x. Right? Okay. And so basically r hat p dot x hat, well, that's just rp over rp dot x hat. That's just going to be x over square root of r squared plus x squared. Okay? So let's put all this together now. So ex is equal to integral of k dq rp squared rp hat dot x hat. Let's plug this all together. So this is going to be k dq divided by let's see, so this is going to be rp squared, which was this thing. So rp, this thing squared is just r squared plus x squared. And this will be x over square root of r squared plus x squared. Okay. So let's go ahead and finish this one off, right? Integral of k dq times x divided by, right, r squared plus x squared to the 3/2 power, right? This appears all the time, stuff that looks like this, so it's just good to get used to that. Okay, now I can't just go ahead and do this integral because I haven't done what dq is going to be. So what's dq? dq is the infinitesimal charge associated with this point right here. And so what am I going to integrate? I'm going to integrate along the circle here. Okay? Maybe I'll call this basically theta, say, some angle theta. All right? I'll integrate along that circle, right? And so basically dq is just going to be basically the charge per unit length, lambda, times the length of this arc right here. This arc right there is just going to be r d theta. Okay, so now let's finally put everything together again. So it's going to be equal to k integral lambda r d theta times x divided by r squared plus x squared to the 3/2 power. And I'm going to integrate along theta, basically from 0 to 2 pi. Theta equals 0 to 2 pi. Okay, now, sorry, should do that right there. Okay, so I've done that now. Okay, so now this looks really complicated. But in respect to theta, there is no theta. This is x, this is x, this is r. Everything is a constant in respect to that. So in fact, this thing here, integrate is basically becomes integral of d theta from 0 to 2 pi. That's just 2 pi. So it's just 2 pi times k lambda r x over r squared plus x squared to the 3/2 power, right? And we can further simplify this if we look up here. Remember what lambda is q over 2 pi r, okay? So this can be, the 2 pi is going to kill that, the 2 pi r is going to kill this, the 2 pi of r and the denominator is going to kill the stuff on the top. So it's going to be k q x over r squared plus x squared to the 3/2 power. And that's it, right, for this one. Okay. So, what do I want to do here? Okay, so that's perfect now. Okay. Before I'm going to return this example in just a second, all right? But before I do, I'm going to basically complete one example where I just missed it, right? So I'm going to look at the following situation, right? Okay. So let's imagine a half ring. That's a half ring right there. Okay. And what I'm going to consider is I'm going to consider a point P in the center of that half ring. Okay. Right. And this thing will have basically some total charge. I'm going to call it this way. It has some total charge Q, right, and some radius R. Right? And so the lambda is going to be Q over pi r, right? So the charge per unit length. Now, it's going to be pi r, not 2 pi r, because this is not a complete circle. It's only half a circle, right? So you can't have the 2 pi r there. All right. So let's go ahead and write this thing down. Again, as previously we discussed, EP is just going to be integral of k dq over r squared r hat. Okay, and if we want to be extremely pedantic about it, we could write this as p. Okay, I'll call this my point p there. All right. Okay, so this is also relatively simple, right? If I want to understand what this thing looks like, okay, I could just basically look at what each of these components are, right? So to do that, it's very useful to consider this in terms of some angle theta here, all right? Okay. Now if I do that, right, the vector will point in this right. That's basically RP vector. RP vector, well, that has some unit, that's some length r, okay, and it's going to be pointing along. Let's see. So let's call this the x-axis, that's the y-axis, so they're both going to be negative, so it's going to be minus cosine theta x hat minus sine theta y hat. Okay, good. All right, so it's pointing down and pointing to the right. Wait, so right, that should be a plus. Good. Okay, so now we can do this. All right, so RP, that's just going to be r, right? And RP hat, well, I'm going to take this divide by little rp, by the length RP, well, that's just going to be cosine theta x hat minus sine theta y hat. All right? Okay. And finally, what I want to say is that, like, if I want to find what dq's are, because that's what I had to find previously, if I break this into tiny bits, there's a dq here, right? You can imagine that this thing right here is a d theta, and so dq is just lambda times the length here, which is capital R d theta, right? Which is going to be something, all right? So that's just what that is. Right? I'll leave it in terms of lambda here. Okay, I got everything I need, right? I have a dq, all these different things. Let's plug it in. Okay, EP vector is equal to integral of, let's see, that's going to be k. Let's do the dq part. That's lambda r d theta divided by rp. Rp squared is capital R squared. That's nice. Rp hat is just this horrible thing right here. Cosine theta x hat minus sine theta y hat. All right. And what am I integrating from? So let's see. Look at this thing. I'm going to integrate from minus pi over 2 to pi over 2 for theta equals that. All right. Okay. So let's go ahead and integrate this thing, right? So if I do that, like basically I'm just doing these two integrals right here. So I want to factor out all these things here. So let's kill some stuff to make it a little easier, cleaner. K lambda over r. Okay, that brings out everything out in front. Okay. Now there's going to be two integrals here. Integral 1 is going to be cosine theta d theta in the x hat direction, and this goes from theta equals minus pi over 2 to pi over 2. And the second one is going to be minus y hat integral from theta equals minus pi over 2 to pi over 2 of basically sine theta d theta. Okay, right? So you know if this is integral of cosine theta, that's just sine theta, right? Evaluate between theta equals minus pi over 2, okay? That's on x hat. Okay, and then the second thing, this thing, is just going to be minus, let me see, it's minus cosine theta. So this converts to a plus here, y hat, okay? Cosine theta, evaluate theta equals minus pi over 2 to pi over 2, okay? Okay, cosine of pi over 2 is cosine 90, that's 0, minus 9, cosine minus 9 is also 0, so this entire thing goes 0. Cosine sine of theta is 1, minus 1, so basically 1 minus 1 is 2. Basically that's 2 x hat. And so we put everything together now, that's just basically 2 k lambda x hat over r. Okay? Oops, let me show that again. All right. So that's relatively simple now. Okay. So that was just a short aside. Now we will go back to that ring that we computed earlier, right? So let me go ahead and talk about that ring a little bit. Okay. So for the ring, okay, we found that E vector is equal to EX, x hat, because the EY component went away, which is going to be equal to K QX over R squared plus X squared to the 3/2 power. All right, that's what we found last time. Okay, so I'm going to basically take this technology and use it up again, right? So this is going to be a short aside for a second. Now let's consider the following. Let's consider a charged disk. Okay, and so a charged disk looks like this. So you can imagine that instead of a ring, and now I have a total disk here. Okay, and again, I'm going to put this position along a symmetry axis at position P at a point X. All right. Okay, and this ring, this disk, has a total charge Q here, all right, and it has a radius capital R again. All right. Okay, so how do I go about solving this problem? Well, the one way I could do this is I can basically break this up to many rings. Okay. The reason why that works is the following, right? So you can recall EP is equal to sum of I EIP, right? This was like the previous thing. It just says you can add all the electric fields together, right? So the equivalent way of saying it is you're integrating over the small electric fields from each ring, okay? These are basically the electric fields for each ring, or each infinitesimal electric field that's associated with it. All right. Okay, so how are we going to do that, right? So in order to do this, right, and the same argument applies as before, basically in canceling out EY and EZ, right? So you can spin this ring around, and then you spin it about 180 degrees. EY maps to minus EY, EZ maps to minus EZ, but they're the same. The situation hasn't changed, and so EY is equal to minus EY, and EZ is equal to minus EZ, and so both those components have to be 0. So same argument applies as before, right? Okay, so all we need to do is now we just figure out the EX component, because that's the only component that will matter, right? So that what that means is basically EX is going to be equal to the integral of DEX's, right? For each one of these rings here. Okay, let's go ahead and figure out how to do this now. All right, so in order to do this correctly, the way to think about this, let me see what the best way of doing this would be. Right, is to take this and imagine, rather than thinking of this big cube, that let's imagine I have a little ring right here. The ring has a radius r and has a charge on it, dq. Okay? So what's that going to be equal? Integral of, let's see, so dEx is, well, actually just take this thing down here, but I'll convert the capital Q to a little dq here. So kx over, now this can be not capital R squared, but little r squared, plus x squared to the 3/2 power times dq. Okay? So you can imagine this thing is a small ring here. And I'm going to give it a very, very, very finite but infinitesimally small distance, all right? Okay, that makes up this ring. And this will be something dr here, okay? Okay, that would be useful in just a second, right? So this is going to be equal to basically kx over r squared plus x squared to the 3/2 power dq. So now I got to figure out what dq is going to be, okay? So what is dq? So this ring here, dq, right, is going to have some charge associated. So the area of the ring is going to be dA times the surface charge density. So it's basically q over the total area. So this is basically area, right? So what is that? Well, what's the total area of a circle? Well, that's going to be pi capital R squared. So it's going to basically be equal to dA times q over pi capital R squared, right? Because that's the total charge of the thing. So now I got to figure out what dA is. dA is this little tiny thing right here. Well, if you unwind this entire thing, it looks like a rectangle with one length is the circumference of the little circle, and the other width is dr. So this is going to be equal to, basically the circumference of a circle is 2 pi little r, q over pi r squared, and the width of that rectangle is a little dr there. Okay, so now let's plug this one in there. Okay, sorry, show that again. Let's plug it in. K x over r squared plus x squared to the 3/2 power. This is an integral now. dq is going to be q over pi capital R squared times 2 pi r dr. Okay? So let's kill the pi's here. And that's the integral we need to do. Okay? Let me show you that right there again. This is the integral we need to do. Okay, slightly nasty, but not the worst, right? Actually, it's easier than the previous one. Okay, so whenever you have something that looks like this, you have an r squared up here. You either do trigonometric identities, but you also notice you have r dr up here. So we're going to basically you'll do a variable substitution, let u equals r squared plus x squared, and then du equals 2r dr. And guess what? Look at that. 2r dr. Okay, so it's going to be equal to. Let's get the limits right. So now that we have this, we're going to integrate all the rings out. So we're going to start with r equals little 0, all the way to capital R equals r. Okay. Okay. So now we have this. We can just write this thing down. Integral of k x over. Let's see. This is u to the 3/2. Okay. Q over r squared, and then this is going to be basically 2r dr, just du. Okay, and I'll keep in mind this r equals 0 to r equals capital R. All right. And if I do that, this is actually a relatively simple integral to integrate. So this is use 3/2. So there's going to be a 1/2 that drops out of this thing with a -1, something like that. So it's going to be basically, let's get this right here now. K Q over R squared checking my notes real quick. Yeah, I made a mistake in my notes, so that's okay. I'm not making a mistake here. X. And then this is going to be equal to 1 over U to the 1/2. So it's 1 over square root of R squared plus X squared. Evaluate at R equals 0 and R equals capital R. And of course, I forgot there's a 1/2 out front, so minus, no, 1/2 out front, so it's -2 up there. Okay, so now we're done. Okay, we can go ahead and compute this thing out now. Yep, okay, so this is just going to be equal to let's see, so I'm going to put a K, a Q, and X over R squared. Let's bring the 2 down as well. Alright, and then the rest of it is that this is going to flip, so so it's going to be basically this term first, so R equals 0 is 1 over X, technically it's 1 over absolute value of X, minus now 1 over square root of capital R, X squared plus R squared. Okay, and that's it. Okay, now if I bring back the pi's here, okay, right, then what we'll notice is that if I define sigma as a surface charge, and it's Q over A, in this case it's Q over pi R squared, okay, this makes it slightly simpler, okay, this just becomes something that looks like this, so it's 2 pi, okay, I have a K there, I'll bring the sigma in as well, alright, and then I have this X term right there, 1 over X. Actually, so I'll be more pedantic. This is actually technically the absolute value of X, right? Absolute value of X minus 1 over square root of X squared plus R squared, right? It's absolute value of X because you took the square of X and then you took the square root of it, right? So the square root always returns positive. Even if X is negative, the square will make you positive X squared, and the square will make the X positive again, right? Okay, so if I do that, all right, okay, that's basically the answer there, and then I can do something tricky. Okay, so if I take R goes to infinity, okay, that makes the charge disk goes to a charged plane, okay. Then I get something very simple now, that I get basically then this is equal to implies that E is equal to, well, first of all, it's only along the x-axis because only EX matters, right? 2 pi K sigma, and now this becomes X over square root over absolute value of X. That's just something called the sine of X, right? Which means that it returns basically +1 if X is positive, -1 if X is negative. All right. Okay, good. All right. So that's basically the first part of of electric fields for continuous charges. Let me just organize my notes really quickly before I leave too many things behind. Okay, let's charge this. Okay, so before I continue, I'm going to refresh my paper, and then we're going to talk a little about something which is an extremely powerful calculational tool, which is one of the centerpieces of this class. Get some paper here. Okay. All right. So now I'm going to discuss something called Gauss's law. Let me bring this down. Okay. All right. So the first thing is that independent of shape, okay, any closed surface has the same number of E field lines that come out of it. Okay, so this is basically it's proportional. It's equal to the charge contained by the surface. Okay, I left a little space here, so I'm going to draw a picture of that. So imagine I have a simple charge, a plus Q here. All right, and it has basically some charges going to come out of it. You can imagine some electric field lines that come out of it like this. I'll draw 6 of them. Okay, all right, nice positive charge. All of these electric field lines come out of it. All right, and I might draw any surface around it, or any other surface around it. I ask, how many field lines are coming out of these different surfaces? The answer is the same in any case, right? I don't care about the shape of the surface is, right? It's still basically 6 surfaces, six charges coming out. You can even imagine like really pathological things that look like this, or like that, for instance, right? Okay. Now, even in that case, what will happen is that if you count the number of things that come out, well, let's see. So in that case, basically, it's still 6, right? So this one comes out here, comes in again, which negates that previous one, and it comes out again. So no matter what, it always basically is equivalent to the number of charges out that come out of it. So what I'm going to do is I'm going to define an electric flux. Okay. And so to define this electric flux, I'm going to define. So let's imagine I have an electric field line here. That's my electric field line. Okay. And I'm going to basically put some surface there, some arbitrarily shaped surface. Okay. And this surface has some normal vector associated with the normal of the surface. Normal of surface. And this has some area, let's say, dA. Right? Okay. Then what will happen is that if I define E dot dA vector, I'm going to define what dA vector is in a second. This is equal to phi, which is electric flux. Okay? And dA vector is just equal to n hat dA. So this is the this is normal to this is normal vector surface. And this is the small area. Right? Generally we're talking about curved surfaces and stuff like that, so it's always useful to think in terms of curved things, right? Okay, so let's consider the simplest case first of all. Let's consider point charge. Okay, so what does a point charge look like? Well, point charge looks like this, so that's a point charge, right? So this is a big plus, okay? And basically, if I consider some surface around it, let's call this the radius r here, okay? Well, what's dA? Well, dA is just going to be dA times the area that times the normal that's times the vector that's normal to the surface. That's just r hat. So I just consider a very simple sphere around it. Okay. And what's the electric field in this case? Well, I know what electric field is because I figured out the last time. This is just going to be equal to k q, right, on this surface over r squared r hat. Right. That was what that was going to be. Okay. So what's going to happen is that if I compute the flux, okay, this is going to be integral over some surface here of E dot dA, right? So this is the surface. I'll call the surface S here, say for instance, all right? Okay, well, we knew what that is, right? That's just this bad boy right here. So it's going to be basically be integral over the surface of K Q over R squared, R hat dotted with R hat dA, okay? That goes to 1, and then you just integrate over the size of the surface, because kq over r squared, r in this case is a constant, so this entire thing is a constant here. That's going to be basically kq over r squared, integral of the surface dA. Well, this thing is just the area of a sphere. That's 4 pi capital R squared, okay? And so that means that phi is equal to 4 pi k q, right? The r squares will kill the r squares on top will kill the r squared off on the bottom. All right. So I'm going to find this thing as q over. Whoops. I'm going to find this thing as q over epsilon naught, right? Where this epsilon naught is equal to 1 over 4 pi k, right? And this has a special name. It's actually the permittivity of free space. But we will not get to that yet. We will get that later. For now, you can think of it as just epsilon naught, right? So, this is true. This, whoops, is true for any closed surface, right? So my charge before, which was surrounded by this this surface, this imaginary surface, I can imagine any surface, and this will still be true, okay? So what that means is that phi, right, the flux is going to be equal to Q inside over epsilon naught, right? So if I ask, for instance, what's the Q inside that? Well, what's the only charge in that? What's that capital charge Q, right? And so this is called Gauss's law, right? And what is nice about that is that this will allow you to solve lots of problems very quickly, right? But you need to know something from the symmetry, okay? So allows you to solve many things quickly, right? But you need additional symmetries. All right? Okay. So let me write this thing down in a way that's like a little clearer. So let's recall what phi is going to be. This is the integral of E over some surface dot dA. That's going to be equal to Q inside over epsilon naught. Right. This is the way almost everyone thinks about Gauss's law. And you will notice that this is an equation here that has left side and right side. So there's the left side here and the right side here. Okay? Now, in order for Gauss's law to work, all right, this side has to be easy. Otherwise, it's impossible. It's either easy or impossible. Okay? And this side is going to be a hard part. So this is going to be easy. For any problem I ask you using Gauss's law, this is going to be easy. And this is going to be hard. Okay? Or could potentially be hard. Okay? All right? Doesn't necessarily have to be hard. Okay. So let's consider an example of this. Right? So let's consider. Okay. So let's consider the infinite plane. Now we had just done this, right? And it wasn't that nice, right? So we had to basically do the electric field from a ring, and then do the electric field, use the rings to do a disk, and then take the disk R to infinity, right? That was like many pages of math to do that. Okay, so we're going to try to do this very quickly using Gauss's law, right? So let's imagine I have a plane here. That's my plane, right? And the infinite plane goes in infinite direction, right? And it has some charge per unit area, sigma. So there's charge per unit area. Okay. All right. And in that case, I have to decide what my surface is going to be, right? So remember I said there's the easy part and the hard part. We have to choose this judiciously so that it is easy. Okay. So here's an easy example. Let me consider a Gaussian surface, right? That penetrates right through. Okay, so that's a Gaussian surface, right? It's a cylinder basically, right? And this cylinder has some radius r and some length L. Okay, this won't matter terribly much actually when we actually do it. Okay, so to do this problem, okay, we need to define an imaginary surface called a Gaussian surface. Okay? And which has to be closed. Right? So it has to contain everything inside of it. Okay? It can't have any leaks or anything else like that. Right? Okay, so this is my Gaussian surface. It's like a little cylinder here, right? Okay? Alright, so how do we figure this out? So we're going to figure out basically what phi is going to be. So phi is going to be, well, let's see, it's going to be the surface integral of S E dot dA, right? And there are several different surfaces here, right? So there's the side here, there's the top, and there's the bottom. Okay? So it's going to be equal to some integral on the top, E dot dA, plus on the side, E dot dA, plus integral on the bottom here, E dot dA. Okay, nice. All right, so we have to use symmetry arguments to make this problem a little simpler, right? And here's how you make the symmetry argument work, right? So you could say that the side terms have to be 0. Now, why is that? Well, let's suppose there was a side term, which means that basically there has to be some electric field which is parallel to the surface of this thing, okay? And so what will happen if I did that is that I could start spinning this thing around, right? And if I spun this thing around, right, so I spin this entire plane around, it will look the same no matter what, right? And so those vectors will map into the negative of those vectors, And because of that, that can't be true. And so what will happen is that these sides cannot have a flux associated with them, right? Okay, so what that means is that at the end of the day, I can only have electric fields that point up and down. So on the other hand, if I was pointing up, right, or down, away from it, okay, so let's say on one side pointing up, on one side pointing down, then if I flip it, then the electric fields still map to each other, and so it actually works all okay. So these two terms here, right, are non-trivial. That means that they have some contribution to it, right? So basically what it means is that E field must be up, and down. And if you think very carefully about it, it turns out that, in fact, basically, if it's up here, then it's down on the bottom. If it's down here, then it's up on the bottom. So they actually flip side across. But that's not really quite necessary yet, if I remember correctly. Okay, so now that's the bit part of it. I have these two components here, all right? Okay, now I just need to figure out basically the right side, which is technically the hard part. Okay, so let's look at this picture here. Okay, there's some area associated with this thing. All right. Okay, and then some surface charge in it. So in fact, if I ask what's the charge contained inside this cylinder, well, it's sigma times the area of the circle part of the cylinder. Right. So that's the hard part here. Right. So that was it. Okay. So in fact, basically, what is Q inside? Well, that's just going to be Q inside is equal to sigma times area of the circle. What's that circle? Look at it again. That circle is radius r, so essentially it's going to be equal to sigma times pi r squared. Okay. All right. So now we're done. Okay. Let's get the fluxes now. Okay, so there are two pieces of that flux. So in fact, this is going to be basically be 2e times the area, which is 2 of the circle, 2e times pi r squared is equal to, right? The Q inside, so this is basically the flux. This is Q inside. Right, Q inside was going to be over epsilon, that is, epsilon naught. This is going to be sigma pi r squared over epsilon naught. Right? Okay, and so now we're done. Shoot, shoot. Okay. E is equal to sigma over 2 epsilon naught, okay, which is equal to 2 pi k sigma, which implies the electric field is going to be equal to 2 pi k sigma times n hat, where this is the normal to the surface. To the cylinder tops, I guess. Well, I'll call it surface. All right? Okay? And so that got exactly the same answer as before, basically. When we did it, we got sine of x. This is the sort of same function sine x, because basically n hat points down the bottom and points up in the top part. Okay? So this is really simple. Look at that. Like 1, 2, 3 lines. 3 lines. We're done. Okay, so that's very nice. Basically, like Gauss's law is extremely powerful. Okay, so we're gonna basically use this for a few different problems. Okay, so let's consider the following. Okay, so in order to make this work, we have to basically use certain geometries that will work with it. So we just did basically planar geometry, but the other one, which is the most common one, is spherical geometry. So let's talk about spherical geometry. All right. for Gauss's law. Okay, so let's go through this. Right. So if I have a spherical geometry, let me imagine. I'll do a simple example first. Let's do a charge Q here. Okay. I cover it with some shell. Right. I'll figure a spherical shell, radius r. Okay. Then basically integral of E dot dA is equal to Q inside over epsilon naught. Again, easy, hard, right? And so, let's do the easy part first. So I chose an appropriate distressed spherical shell. And as I make the argument that like if I take the shell and I spin it around, rotate it basically, then what that means is that all the electric fields have to be pointing outward and they have to be constant, right? If they were not, then basically if these were not constant, if I rotate them down, then the non-constant vectors will rotate into each other. And that would not be simply not be true, right? And so basically these are all constant. So this is going to be simply E dot A r hat. Okay, so this is just going to be EA is equal to, so that's the easy part. What's EA? E times 4 pi r squared is equal to, now Q inside, well, this one's easy, right? There's only one charge Q there, so that's going to be Q over epsilon naught, right? So this can be basically be let's see, it's going to be Q over 4 pi epsilon naught r squared, which is just KQ over r squared, which is what we knew already, okay? Sorry, which is what we knew already, basically. This is Coulomb's law again, okay? Okay. And so E is equal to KQ over r squared, r hat, right? Because r hat's the normal vector there. Okay. Okay, so let's try the next one. So uniformly charged shell. Let's get some new paper here. Shell. Okay. So let's imagine that I have a shell now. It's a round shell, right? And I'm going to just attach a lot of Q on the surface of it. That's Q there, right? And I want to basically figure out what the electric field of this thing looks like, right? Okay. So again, basically integral of E dot dA is equal to Q inside over epsilon naught, okay? And I'm going to pick I need to pick a shell, but in fact there's actually two cases, right? So if this shell has some radius r here, okay, then basically I can pick shells like that look like this, okay, so r greater than r, and I can pick shells look like that. This is r less than capital R, right? And I have to do these two cases separately, right? So I'll do the outside case first, right? So for r greater than r, the outside case, right? Well, same thing again, it's spherical, and so all the electric fields are constant. It's going to be E times 4 pi r squared is equal to Q inside over epsilon naught. What's Q inside for the big shell? Well, that's just Q. Q over epsilon naught. And so if you go through this again, you get basically E is equal to KQ over r squared r hat, right? So same as before. Now for r less than r, on the other hand, right, this side stays the same, right? The left-hand side stays the same. It's E, again, times 4 pi r squared. This is equal to Q inside. So what's Q inside for a charged cell? It is 0. There's no charge in it. So that's 0 over epsilon naught. So in fact, in this case, this gives me that E is equal to 0 for r less than capital R. All right? Okay, so that's slightly different, right? As before. Okay. And so basically what's interesting about this is that inside a shell, right, that E is turns out to be 0, right? Okay, so let's do one more case. Let me think about this. Yeah, let's do one more case like this, okay? Or uniformly charge sphere. Okay? Right. So this is the one that everyone cuts their teeth on, right? So we're going to take, instead of a shell, now we have a sphere, add some radius r, solid all the way through, and I uniform distribute charge q over this entire sphere, right? So if I do that, basically I can define a charge per unit volume. Rho is q over v, so this is charge per unit volume. Right? Right. Okay. Two other things. Okay. So I have to find this charge per unit volume here. Okay, and then right. What I want to do here? Oh yeah, that's right. So I have this charge per unit volume. Right. This is the volume here. So for volume for a sphere is q over 4/3 pi capital R cube. Okay, so you should get your areas and volumes of spheres packed away. Area of a sphere is 4 pi R squared. Volume of a sphere is 4/3 pi R cube. Okay, right. Always something useful to have. Right? Okay, so we'll do two examples again. Right. So first we'll do R greater than R. Okay. Sphere looks like that, right? So in that case, all right, it's basically you're gonna get E dot dA is equal to Q inside over epsilon naught. This thing always turns out the same thing, all right? Because it's spherical symmetry. This is E times 4 pi R squared. Now what's Q inside? This one, in this case, is easy, right? What's contained inside here is totally charged Q. So Q over epsilon naught. And so again, if you work this out, this E is equal to KQ over R squared again. Okay? All right, simple enough. Now, for R less than R. Okay? The right-hand side is the same as before. It's E 4 pi R squared, right? That's what makes this Gauss law so powerful, right? I mean, left hand side is the same as before. That's what makes Gauss law so powerful. Again, it's 4 pi R squared again. But now, I've set this equal to something. I've set a Q inside. What is Q inside for this one? Well, it's not all of Q because not all of Q is contained. What it is that it is the integral of rho dV, okay, where the volume is inside, or you think of it as rho times V of R, okay? Divided by epsilon naught, right? So this is basically rho. What's the volume of a small sphere? 4/3 pi R cubed divided by epsilon naught, okay? Let's plug in what rho is out here. This is Q over 4/3 pi R cube. Let's bring a 1 over epsilon naught out here. 4/3 pi little r cube. The 4/3 pi cancel each other out. And so you end up getting something which is E 4 pi r squared is equal to Q over epsilon naught R cube over capital R cube, okay? And so this thing will kill off two fractions of that. And so you get basically Q over 4 pi epsilon naught R over R cubed is E. Okay? All right. Beautiful. Okay. So, before I close, I want to discuss two more examples, which are relevant, right? So the first example I want to discuss is I want to discuss a let's say uniformly charged cylinder. Okay, all right. So let me think about this. That is a bit of a pain because I must just let's just try it. Let's just see what it does. Okay. So let's imagine I have a uniform charge cylinder. Okay. And the problem is this goes out to infinity, so that's why I generally don't like these things. But I mean, like, that's just life, right? Got to deal with it sometimes. Or sorry, uniform charge cylinder, right? And I'll define a charge per unit volume rho in here. Okay, so that's charge per unit volume. Okay, we're going to do something tricky because it's infinitely charged, so you got to be careful with it. And so what I want to do now is I want to basically figure out what the electric field of this thing is, right? So this uniform charge cylinder has some radius r here, okay? So again, I'll do the same thing. Integral of E dot dA is equal to Q inside over epsilon naught, all right? Okay, so I have to pick something that's appropriate for it, and I'm going to pick two different choices. First thing I'm going to do, I'm going to pick a surface look like this. Okay, so this has some length L here, say, and this has some radius R. And then the next example, I'm going to take a surface look like this, something smaller. Okay. This is basically another length distance, little r again. Okay, so let's look at the big one first. R greater than capital R. All right. Well, this thing, stuff can't go out of the top of this thing. All right, because I can slide this thing up and down. All right, and if I slide this thing up and down, it's the same problem again because this is an infinitely long cylinder. And so anything that moves up will be mapped onto something that points down the opposite direction eventually. And so basically it has to go away, right? Similarly, if it was all pointing straight up, right, I can flip the entire thing and I get the same problem again. And so those things will map. So what that means is that basically whatever happens, the electric field has to be pointing along the size of the cylinder, right? Okay, that simplifies my life a little bit, right? So it's going to be E times the area of the side cylinder. Well, the area of the side cylinder is basically the length times the width. The length is going to be 2 pi r times the width is going to be L. This is going to be equal to, now what's Q inside this thing? Well, that's just going to be the density, rho, times the area of a cylinder, that's pi r squared times L, all right, over epsilon naught, okay? And so these L's have to kill each other, and so you end up getting something pretty simple now. This is E is equal to, let's kill the pi's as well. Pi's gone as well. Let's see, E is equal to, let's see, so this is 2 epsilon naught R rho R squared. Oh yeah, that actually works out really nicely. Okay, good. All right. So, and then you want to get the vector components, right? E vector is equal to rho r squared over 2 epsilon naught r hat. Okay, pointing outward. Okay, next thing. Okay, let's imagine if I take a smaller cylinder in there, the inside, so r less than capital R. And so in that case, what I have is the following. I have the left-hand side stays the same as before. Is E 2 pi r L is equal to. Now let's look at the right-hand side. Okay, right-hand side is the hard part now. Now this doesn't contain the entire charge here, but it contains basically a small amount, right? This is R, so it's going to be rho times pi little r squared over L over epsilon naught, okay? And so basically you can work this out again, right? E is equal to, cancel the L's out as well, rho R, yep, over 2 epsilon naught, right? And so if you want to work it out, E vector is equal to rho R over 2 epsilon naught R half. Okay? Beautiful. Look at that. Like, solved the entire problem in just a few lines, right? Okay. So that's it for this lecture. And so next week we'll basically start talking about electric potentials.